Hi class, in this video here we're going to look at section 3.2 and it's about comparing the infinite. And what we're going to be doing here is we're going to be pairing up collections via a one-to-one correspondence. Okay. All right, so what are we going to start with? We're going to start by talking about counting, again, as we did in the last section. Okay, so we use this phrase here, cardinality of a set. Okay, so cardinality means the number of things in a set. And this is understanding that the set may contain infinite many things. Okay, so, all right, but if a set contains only finitely many things, like for example, 50 things, then its cardinality is just the number of things in the set. Okay, so it's just the number in there. Okay, so the count. So how many objects are in the set? So two sets have the same cardinality if there is a one-to-one correspondence between the elements of one set and the elements of another set. Okay, so if you can map them one-to-one, they have the same cardinality. All right, so here's an example. So two sets have the same cardinality if there's one-to-one correspondence between the elements in one set and the elements of another set. Okay, such that if you have the set of stars on the US flag, there's 50 of them. And the set of states in the United States, there's 50 elements in this set. There's 50 elements in this set. Like, for example, you could be like, star 1 maps to Alaska. Star 2 maps to Washington. Star 3 to Oregon. Star 4 to California, and so on. All right. In this case, both sets have finite cardinality, and the cardinality of those sets equal 50. They're both the same number of elements. So there could be a one-to-one correspondence between them. But now what we're going to talk about is what happens if the cardinality of sets is infinite. So they have an infinite many objects in them. Okay. All right. So here's this thing we're going to start with. All right. Is this section looks to show a correspondence between two sets. Okay. So the first set we're going to have is the set of natural numbers. Okay, so the natural numbers are numbers 1, 2, 3, 4, 5, 6, 7, so on. And then we want to compare the collection of natural numbers with the set, but with the number 1 removed. Okay, so we have this first set. It goes 1, 2, 3, 4, 5, 6, 7, and it keeps going on forever and ever and ever to infinity. And then this other set, 2, 3, 4, 5, 5, 6, 7, and it keeps going on for forever and ever. Okay. So do these two sets have the same cardinality? Okay, so the same number of elements. So what's interesting here is our intuition is pulled in two directions. One direction is the infinity is an infinity camp, like, well, set 1 has an infinite number of elements in it. Set 2 also has an infinite number of elements. Doesn't really matter where they begin. But the other one takeaway is, I don't know, take one away, you have one less school. So like, well, there's obviously one less number in this set than in this set, so it can have the same cardinality. All right, well, this is how we approach it, right? So sets have the same cardinality if you can form a one-to-one correspondence. All right. So if we are from the take one away school, we have one less. It may appear that there cannot be a one-to-one correspondence between the two sets. All right, so that is if we paired the numbers this way. Okay, so I'm going to pair, look, this one does have 1, but I'll pair 2 to 2, 3 to 3, 4 to 4, and like they do not have the same cardinality because my pairing will go on forever, and this one will have one extra number. All right. Well, actually, it turns out, in fact, a one-to-one correspondence between these two sets does exist. Okay, so even though this starts 1, 2, 3 all the way to infinity, this goes 2, 3 all the way to infinity. So even though it would seem that there is one less element here, they actually have the same cardinality. Okay, they both go on to infinity, and you can map, you can form the one-to-one correspondence. All right. And this isn't going to surprise people who are members of the infinity is infinity camp. Okay, so we illustrate it this way. You shift it. Okay, so you take the first element of the natural numbers 1 and you map it to 2. You go 2 to 3, 3 to 4, 4 to 5. Okay. So what this means is, like, another way you could illustrate it is like if you pull a ball out of the natural number, if you have all the natural numbers in a barrel and you have all that other set 2 to infinity in the other barrel, you could pull numbers out one at a time and you could map them perfectly. Okay. All right. So we can use the following symbol to express a correspondence, this double arrow here. All right, this symbol compactly illustrates which numbers are paired. So what's going on here is the way we're pairing it is number or element n, quote unquote, in the first set, the natural numbers, is mapped to n plus 1. Okay, So this means that the number n from the natural numbers is paired with the number n plus 1 from the new set barrel. Once we know which number n represents, we immediately know it's me. Like, for example, this is how I mapped it. 1, that's my n, goes to n plus 1, goes to 2 in the second barrel. See what I mean here? 1 goes to 2, 2 goes to 3. I have this nice mathematical relationship here. And you can see you can form this relationship forever. Whatever you tell me the number is, like if I pick number 1 million, that maps to 1,000,001 in the next set. So there is a one-to-one correspondence. Even though it seems like, well, it's always one number higher, it's like, yeah, but the numbers still go to infinity. So like whatever number you can pick, I can immediately pick the next number. Okay. So there is a one-to-one correspondence there. Okay. And like that was the quick trick to map it. Okay. Both sets have the same cardinality. They have the same number of this is going to sound weird, but they have the same number of infinite members. Okay. Their infinities are the same. Let's do another one just so you can kind of see this. Okay. So I have two Mindscape problems for you here. Okay. So let's let E stand for the set of all even natural numbers. So I have this new set E, which is the numbers 2, 4, 6, 8, 10, 12, 14, blah, 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 forever. Okay. Show that this set E and the set of all natural numbers have the same cardinality by describing an explicit one-to-one correspondence between the two numbers. Okay. So what that means is you have to figure out some tricky way to map the numbers from each other. So look, I'm going to start with the natural number 1, and I need it to map to 2. I'm going to start with the natural number 2. I need to map to 4. 3 needs to map to 6. 4 needs to map to 8. What would the natural number 5 map to? 10. What would the natural number 6 match to? 12. So you can see here is that the natural number n, whatever it is, matches to 2 times n, right? 1 goes to 2, 2 to 4, 3 to 6. You see what I'm doing? I'm doubling it, okay? And so whatever natural number you pick, I can map it to whatever number in E. And I know it seems weird. You might be like, well, E only has half as many numbers as n. Like the way you would think about it is like, well, what is half of infinity? It's still infinity, right? So they have the same, it goes on forever. So you can still form this correspondence. Whatever natural number you pick, whatever natural number you tell me, like if you were to say natural number 1 million, I would say, well, that maps to 2 million in the new set. 20 billion in the natural numbers would map to 40 billion in the new set. Okay, whatever number you can tell me, I can show you the one-to-one correspondence. I can find the exact one number it matches to. Here's another one so you can see it. Let's let this new set S stand for the set of all natural numbers that are perfect squares, okay? So these are numbers like 1, 4, 9, 16, 25, 36, 49, 64, so on, 81, 100, okay? Show that set S and the set of natural numbers have the same cardinality, okay? So there's the same number of elements, okay? By describing an explicit one-to-one correspondence between the two. And look, all the perfect squares are just the squares of the natural numbers, okay? So like 1 corresponds to 1. 2, well, what is 2 squared? 4. What is 3 squared? 9. 4 squared? 16, so on. So the mapping, the correspondence here is whatever n you give me, well, just what it maps to in the new set is n squared. That's it, okay? That's how we're mapping. N goes to n, maps to n squared or n times n. And while it might seem that S has not as many elements in it as this one, well, remember they both have infinite many elements in it. Okay, these numbers just keep going on and on forever. And so this tricky mapping here, this clever way to map and show how the correspondence goes, shows us that these two sets have the same cardinality, the same number of elements, an infinite number of elements. Okay. Even though it might not intuitively seem that way. And what we'll do in the next section is show you that there's actually different levels of infinity. And maybe, one set that has an infinite number of elements cannot be mapped to another set that also has an infinite number of elements. All right, class. Thank you very much.